different parts of our brain that are responsible for different tasks, and they have different structures and different complexities. The next point is being able to create a bridge between different modalities is very helpful. You know, there is this famous story about Rosetta Stone, which was a stone found in Egypt that for the first time allowed for understanding of certain languages. And it was a revolution because it was something that allowed us to have access to that, to a couple of new languages. And before that, it was not possible to understand some or comprehend some of these languages. Now, if you have a huge data set of text, and if you also have a huge data set of images, it will not be obvious to create parallels and connections between image and text. But for that, we need to have maps. We need to have certain images with textual descriptions, and vice versa. So this is also a key. This is a very important point that, I mean, this is, again, something that is very fundamental, but people don't talk about. And similar to that, having a shared representation space is crucial. I mean, it's not crucial, but it is very important. This image is from a paper that we wrote, my co-authors and I wrote in published in 2010, 15 years ago, which was the first paper on mapping between different modalities. And the way we were able to achieve mapping from image space to sentence space and back was to come up with a shared meaning space. Back then, we were not referring this as a representation space, but rather we refer to it as meaning space. And this meaning space, we constructed it completely manually. So we had a bunch of object detectors that were able to look at image and tell us whether a certain object is present in the image or not. And we trained it to tell us whether a certain verb is also present. And basically, we created this meaning space of objects, subjects, objects, and verbs. And then we were also able to create a connection between our sentence space and the meaning space, right? And as soon as we were able to create these two connections, we were able to connect images and sentences. So we created demos that given textual descriptions, we can create images, and given images, we can create textual descriptions. I mean, the results were very primitive back then, but given the tools and techniques that we were using, I think the results were reasonable. But then the key contribution here is to create this shared representation space. And now, when we work on multimodality, everywhere we observe the same pattern. And then, when we use these shared representation spaces, we get some emergent properties, right? Some new capabilities emerge. For example, if you have a bunch of parallel image and text descriptions, images and text descriptions, you can create you can learn a shared representation space. And then if you have a bunch of parallel text and voice samples, you can also use the same representation space to project them. And then, as a byproduct, you will also get a connection between images and voice, right? Even though you have not had any direct connections between the two spaces. And of course, this is going to be more efficient if we have direct connection, but even if we don't, there are tricks to, to be connected, to make them connected. But one thing that was missing in this work from 2010 was that there was no end-to-end training. So the projection between image space and meaning space was fixed, or basically trained separately. From meaning space to sentence space, it was also trained separately. And the representation space was completely designed manually, right? We didn't allow the representation space to improve over time. But later, people developed techniques that allowed for updating these projections and updating these representation spaces. So there was a lot of room for improvements. And in fact, we observed a lot of improvement in subsequent works. And then if you have multiple modalities, there are always these tricks that, for example, if you want to translate some text, you can use speech recognition. You can, to transcribe the input voice. And then you can use translation, machine translation, to translate from the source language to the target language. And then you can use text-to-speech to create speech, right? But this is not as good as directly translating voice. Because if you take my voice and translate it through that upper process, you will lose a lot of details that are present in my voice, right? My tone, my accent, a lot of these details. But then if you have, if you use a direct translation, you will be able to preserve these sources of information. So it makes the translation richer. But then it is also more difficult. It is difficult both computationally, and you will need to have more parallel data. You will need to have more data. In fact, you have a huge amount of voice data that is available, but we don't have a huge amount of parallel voice data. So basically, there is this trade-off that if you want to create a direct connection, you will have less data available. Another revolution in multimodality was the introduction of generative multimodality. If you think about this question that I wrote on the top, what is the diameter of the Earth? Of course, most of you guys don't know the exact diameter, but if you think a little bit, you can most likely tell that it is not 3,000 kilometers, it is also not 4,000 kilometers, it is also not 40,000 kilometers, right? So it is 12,000 kilometers. So even though you don't know the diameter of the Earth, you can get this question answered correctly. But if I ask you a written question, that what is the diameter of the Earth, you are not probably going to be able to write it down accurately, right? So if you think about it, the top question, the multiple choice question, is worth only 2 bits because there are only 4 choices. But the middle question is worth way more because you need, I don't know, maybe 16 bits to store that number. So basically, it is harder to do generation than to do classification. But because it is harder, you can also make more mistakes and learn from your mistakes. Okay, what's happening here? That's okay. While you try to fix this, I will continue. It is good to expose yourself to a situation where you can make more mistakes. Because the more mistakes you make, the more feedback you take, and the more feedback you take, the more you learn, right? So, generative multimodality, it has had a lot of interesting characteristics and use cases, but one very important side effect of generative models have been this very fact that it allows you to make more mistakes and learn more from your mistakes. And you know, the same thing that is true for writing down some textual description is also true for generating images. In fact, when you generate some image, the bandwidth of the data is way more. So you may make way more mistakes. You know, there are a lot of subtle details in the image that you generate. And because of all of those subtle details, you are going to make a lot of subtle mistakes, and you're going to get feedback from those mistakes. So generative multimodality allows for better learning and better understanding of the topic of interest. Is it okay? Okay, perfect. Yeah. So if a sentence is worth 20 bytes and the answer is worth 10 bytes, you know, an image is worth 1 megabyte, right? So it's a much bigger bandwidth. So you learn way more. So the sixth thing is the revolution of self-supervision. You know, traditionally, the way people looked at machine learning was you have a data set of X and Y, where X is the input, Y is the output, and then you can input X, you learn a function that inputs X and outputs Y, right? That's the traditional way. But then there was this revolution when people realized that getting data, I mean, there is not enough data that is labeled this way. So people thought about how they can use an unlabeled data to train a supervised model. A lot of tricks were used. One trick was this masked language modeling process on the left, where you have this sentence, and each word in this sentence can be seen as a target. So for example, for this sentence, Doha is the capital of Qatar, you mask the word capital and input the words Doha is the, and then blank, of Qatar. And then you let the model learn to predict capital, right? So this way, this simple sentence is turned into 7 pairs of inputs and outputs, right? And this allows you to learn a whole lot of stuff. Same thing is true for super resolution, where if you have this ground truth image, you can deliberately downsample the image and use it as input, and then use the ground truth as output, right? So like you input this 8x8 image, and then your model has to learn to create this 32x32 image. So you use the same data for training without having it labeled. Self-supervision was a revolution because it allowed this access to a huge ocean of unlabeled data that has always been available on the web. And it allowed models to become more complex and learn more stuff. But then this is the positive side, that you have more data to train. But the negative side is the fact that this data is not clean. For example, when we trained the language model of Fanar, we learned using a lot of data from, for example, Reddit. And a lot of data from Reddit is low quality. And that affected our model. So we had to manually filter some of that data. Right? And even if we filter that data, that is not even enough. So we always have to use some sort of fine-tuning using high-quality data to be able to get the model to do the right thing. Otherwise, it learns from the web, and if a model learns from the web, how it is going to behave, right? It's not going to behave appropriately. There are a lot of other techniques that employ self-supervision. For example, SimCLR it takes two different views of the same image. Like it takes this image, creates two different views of this image by cropping and changing the color and applying some transformation. And then it passes them through some convolutional neural network, and it forces the results to be close. Right? And the results from this image to images taken from other sources to be different. Right? And then if you do this, you will start to learn a representation that is robust to these transformations. You know, so basically, you just need to have images. And if you use these images to train this model, the model gives you some representation that you can very easily use for some downstream tasks. For example, for image classification or other tasks. And this was also a very important advancement. And then there is BYOL, which uses a kind of a similar process, but there are two networks moving together, and one network is trying to mimic another network. But the bottom line is these are all self-supervised representation learning techniques. Another revolution was the emergence of transformers and the concept of attention. You can have single modality attention, which is what happens in text modality and image modality alone. But then there is also cross-modal attention, which means that, for example, if you have a text and an associated image, when you look at the text, when you look at a word in the text, a certain part of the image lights up, right? And you pay attention to that part. And this also greatly helps, it increases the connection between the image modality and the text modality. The eighth point is the idea of contrastive learning, where the idea is if you want to project two modalities to each other, or for example, there are a lot of situations where you don't have an anchor point for what the distance should be, but you sometimes know that some objects, some pairs of examples should be close to each other. So let me explain. So imagine we have this person, and we have two images from this person. We call this image anchor image, and we call this other image positive image. And we take an image from some other person, and we call it negative image. Right? So these two images belong to the same person, but these two images belong to different people. Right? So we don't know what the distance between this image and this image should be in our representation. And we don't know what the distance between this image and this image should be in our representation. But what we know is this image and this image have to be closer to each other than this image and this image. So basically, if the negative point, which is this image in here, in this example, is closer to the anchor point than the positive point, you learn something so that you fix this, right? And contrastive learning is also very effective. The next point is the importance of causality, prescriptive analytics, and understanding of corner cases, because the models that we are using, if they're only trained on fixed data sets, they will only learn through understanding correlations. They will not understand causation. But if a model wants to act in an environment, it has to also be able to understand the consequences of its actions, right? For example, if you watch a person driving for hundreds of hours, you're not going to learn to drive. But if you try to drive yourself for 2 hours, you kind of start to learn to drive. The reason is when you drive yourself, you feel the consequences of your actions. But when you see somebody else driving, you don't feel the consequences of their actions because you are not the person who's making those decisions and taking those actions, right? So if you want a language model or whatever model to be able to thrive in a complex world and make actions, we need to have some notion of causality. And for that, we need to allow the model to interact with some space, right? And a lot of times it is not easy, but if we have simulation, we can allow the model to, to perform, some interaction with in the simulation environments. Also, we are observing that a lot of models like the O1 model and DeepSeek model, they are improving because they are improving their search space. I mean, they're improving their search during the inference time. And they're also using Monte Carlo tree search to basically create a foresight, right? To be able to see farther in the future. So this is also a very important development. And it is also necessary for especially agents that want to interact. So the last topic is about the future of multimodality. Definitely AI has a potential to be stronger than humans because AI can have direct access to a lot of different modalities, right? We don't have, inherent ability to understand depth maps. I mean, sorry, not depth maps, but thermal images, for example, or radar images, or electromagnetic waves, or chemical stuff, right? But AI can. So that's a very important thing to allow AI to access more modalities. And then, because we cannot let an AI to create mess in the real world, we should allow the AI to interact with some simulated environments, like, for example, a computer game. And that is also going to be very important. In fact, the quality of, the higher quality we can create computer games, and the higher quality we can create simulation environments, the better our AIs are gonna behave. Because we can test our AIs in those simulation environments, and if the simulation environments are accurate, our AI is gonna learn to behave appropriately in the real world, right? And then there are gonna be a lot of corner cases that in order to have a reliable and robust system, you need to be able to handle all of those corner cases. So those corner cases can be found in simulation environments. Like, for example, if you have a self-driving car, a situation where you hit a person is a very useful situation because you learn a lot from that, but you cannot allow this to happen in real life, right? So you should basically try to find these scenarios in in simulated environments. Also, if you look at the history of AI, 100 years ago, everybody used to think that AI is having a good ability, a strong ability for deduction, right? Like mathematics and deductive reasoning and things like that. And then it took maybe 70, 80 years, and people in AI switched from deduction to induction, right? They said, let's leave alone all of those algorithms and all of those search techniques and stuff, and let's focus on learning. And there was a period of time, maybe 10 years ago, 15 years ago, that everything was learning, right? You just throw a machine learning model to some task and basically learn. It used to do a good job. But now people are realizing that they should marry induction and deduction together. So we rely a lot on induction, which means learning, by fitting a 10 billion parameter model to 1 trillion tokens. And then we also use deduction, where at the inference time, we try to create an output that is logically sound, right? And also human in the loop generation is important because the model has to generate something, and sometimes, you are not satisfied with what the model has generated, so you have to give it feedback. So the model has to be able to get feedback from people and adapt to the requests of the user. Anyways, that was it. Again, feel free to message me if you want us to meet. And we have some interesting research work at QCRI. And it would be, we would be happy to have some internships to host some of you guys for longer. Okay, thank you very much. If you have any questions, thank you. Feel free to ask your questions. Yes.
Self-supervision and contrastive learning, right? Because in self-supervision, we are using contrastive learning tasks as well in SimCLR and so on. So I think it would be interesting that if you could elaborate on that, why you made the distinction as two slots. And question number 2 is that you said in the future of multimodality, the physical simulation is the key. But can you elaborate on that? Do you mean that physical simulation in the sense that as a test bed, just evaluating, or do you mean that we can use these physics-based simulations, such as physics-informed neural networks and so on, during training to have better models? Thank you.
Okay, so the first question was why we see self-supervision and contrastive learning as two separate things, right? The reason is there are a lot of situations that you use self-supervision, but you don't use contrastive learning. For example, the examples that I gave, super resolution and mass language modelings are two examples where you use self-supervision, but you don't use contrastive learning. And there are also cases where you use contrastive learning, but you don't use self-supervision. So a lot of times these two tricks come together, but not all the time. Regarding your second question about what is the point about physical simulation, right? AI is stuck in the computer, right? We don't have AI, we don't interact with robots, right? You don't have a robot that would go around and do chores and do all sorts of stuff. The reason is, even though AI can potentially, has a very high potential for contributing to robotics, but we have not figured it out. Honestly, that is the real problem. And the reason is, we have not modeled the world accurately enough. Right? So for example, if you have a robot, I as a person, if I want to interact with something, for example, I want to interact with this object, I very carefully measure the amount of force, I understand the weight, I understand the composition, a lot of stuff are there that I understand. And those are required for me to be able to carefully and accurately interact with this object. But AI cannot do this very well because you have not taught it to do so, right? We have trillions of tokens to train from the web. We have billions of images to train, to use for training in the web. But we don't have like billions of instances of robots interacting with physical objects to learn from. And I think the missing chain, the missing part in this chain is not having a good physical simulation. Because if you have a physical simulation, you are not going to have any limitation in how much you want to interact with the world, right? Like your robot can, interact with this object hundreds of times, thousands of times, and it can break the objects hundreds of times, and it is not going to be costly. But you cannot afford breaking this object down. In real life. Yes. And then you. No, go ahead.
Thank you. So I have a comment and a question. So I started the comment first. So early in the talk, you mentioned that we need to treat every modality separately, right? And you cited the brain as an example. So my comment is I think that I'll make an argument that the brain is actually an example for why we may not need to do that. Because in the brain, if you look into the cortex, it's homogeneous everywhere. It comprises of these vertical columns that are the same. So it seems that the brain applies the same learning mechanisms to every modality. It doesn't really distinguish.
But this is proven to be not the case.
Is it?
Yeah. Like different parts of brain learn differently.
Yeah. There are areas that specialize, like of course there are the area specializes to vision, etc. But anatomically, they are the same. Like they comprise of the same column, the same vertical column, so they apply the same learning mechanism to every modality. I think,
like similarly, you can make the argument that all of these machine learning models are using floating points, right? So I can argue that they're all identical.
I wouldn't compare the two. I would say maybe even in AI, the analogy would be that we are converging on similar architectures for all of the modalities. So that might be. But that's
sure.
It's a point of discussion. I agree with you. Yeah. But my question is, so when you talked about emerging abilities, you mentioned that when you learn this joint representation between images and text, which today we would do something like a clip style model, right? Then you said that voice capability emerges. I didn't get that part. Can you just elaborate on this?
Yes. So the point I tried to make was if you learn a shared representation space that connects images and text, and then you learn in the same representation space, you also try to connect text and video, then the video, voice, is also mapped to the same shared representation space, right? So you get, this connection between image space and voice space. Right.
So you mean then we could train like another encoder for voice that maps to the same?
Yes.
Yeah.
Yes.
Okay.
Okay. Yes. Go
ahead. Thank you for the talk. So there's a lot of research going on in robot foundation models, and so they are training on large amount of robotic data, and they are creating these like vision language action models. I wanted your opinion on that, and is that a promising direction?
Yes. Yeah, that is definitely a promising direction because robotics are going to become very important, like you are gonna, in the future, you are gonna have assistant robots that are gonna do a lot of your personal works. So that has not been unlocked yet, even though a lot of stuff have been unlocked in AI. but that is going to be unlocked within the next 10 years.
Yeah, Mike, I asked this question because so the vision language action models, they have this like end-to-end system, but people argue that it would be better to use like use traditional control as well, like incorporate like a model
Definitely.
predictive control or stuff like that. So
Yes, definitely. The reason that I separated all of these modalities was because I wanted to explain that each of the modalities should be treated differently, right? One important modality is the control modality. I didn't discuss it here. But in control, you have feedback, you have actions, you have tracking, a lot of those stuff. So if you want to have a model that is going to behave in the real world, especially if it is going to behave quickly, you need to have a lot of control elements in it.
thank you.
You're welcome. First him and then, sorry.
Hello, thank you for your presentation. So in the company I worked in previously, we developed a simulation script to simulate printed paper. To the point it was really, you can't differentiate it between real paper and simulated paper to train donut OCR model. The point is we
To train
spent
OCR. To train OCR.
donut OCR model. Yeah, OCR model. Yeah.
Okay.
Point is, we spent about 3 months and money and resources on this, where we could label 3,000 or 4,000 images. So for now, is it worth it to simulate visual scene? Like for physical simulation, yeah, it makes sense because there's something we can't measure, like pressure and this stuff. But for visual simulation, is it worth it for now? For cost?
Is it worth what exactly?
Costly. Like we could take images and label them.
Yes.
Or we could spend a lot of time to create simulation. I want to simulate car detection model. I simulate a car moving and with a blender. Or
I
something.
see. Yeah, I see your point. See, here there is a trade-off, right, between the amount of effort that you put into this simulation and what you get out of the simulation. So the easiest way to do to prepare data is to just annotate a bunch of examples. If you want to create a simulation environment, the positive side is you're gonna get a lot of data out of your simulation environment. You're basically gonna have access to unlimited amount of data. But then the downside is the simulation process, the development of the simulation environment itself is very costly, right? So you need to figure out how deep you want to go, right? If you want to go very deep, you have to spend a lot of effort into making your simulation as realistic as possible. Take into account all of the complexities that happen in the real world in your simulation environment. But a lot of times it is not worth it, right? I cannot comment whether in your specific application it is gonna worth it or not. But if somebody wants to do a very, very serious job, the only way is really to, especially something that has interaction with the world. The best way is to have a simulation environment.
Thank you very much.
So I wanted to ask about in the self-supervision.
Yes.
You talked about the access to unavailable data.
Yes.
And in some fields, for example, like in weather satellite imagery, we need to annotate data, but it is always done by some experts.
Yes.
So my question is there a way to, let's say, to make this automatized somehow, or to build a model that learns how to annotate these images, so I can do it quickly and build a big data set of annotated data for a specific field?
Yeah, that's a very good point. Yes, the answer is people have started, people in a lot of environments, people have stopped labeling things manually, right? they do label stuff, for example, with language models, right? And the funny thing is that you use the same model to label some data so that you use that data to train the model itself, right? And it completely makes sense. And this is the idea behind this Monte Carlo tree search thing that I talked about. You know, this AlphaGo work, you know, the way it works is the computer plays with itself. And it will think, you know, a lot to see like 10 steps forward. And if we try to learn to predict 10 steps forward without going practically 10 steps forward, right? Okay. So it's like kind of a bootstrapping process. But basically the answer is in a lot of situations, you can teach yourself, right? Like a kid, for example, that sits down and plays with math and learns all of the rules of math and everything. You can do that, right? No, I mean, without any labeled examples or anything. But that is another degree of self-supervision, you know, a higher degree of self-supervision.
Thank you.
Thank you. Okay, I think
Hello.
we are done. Or is there another question? Oh, yes, sorry, I apologize.
It's all right. Thank you for the great talk. My question is similar to the one asked before. Like he said, some domains don't have a lot of annotated data available. So I have worked with CLIP and its variation like BLIP and SimCLR. So the problem with that, these models is we use the pre-trained versions and then fine-tune them on our specific data set. So as we don't have a lot of data set in some domains like healthcare and other, so the model, it quickly overfits on the data. It forgets its previous learning as well and performs really bad on the other data as well. So there are some techniques for that, like gradient accumulation and other things like augmenting the data, but still it does not perform that well. So what can be done to mitigate these problems? Yes.
Yes. So this is a very classic problem in AI, right? You start, I mean, it's not a specific problem that you have. It's like a very classic problem. Basically, you want to be able to do domain shift without losing ability on the original domain, right? Yeah, I mean, there are all sorts of techniques like regularization, manual, you know, data synthesis techniques. I mean, I think after the talk, we can talk to each other, I mean, in person, and I can maybe ask more questions about the details of your problem and give you more detailed description.
Thank you.
Thank you. Any other question? There. Or is there anybody here who has a question? Okay, yeah, there.
Hi, thanks for a nice presentation. I wonder this concept, how could be applicable in the field of brain-computer interface or brain-robot interface, since the brain signals is rarely you have long data acquisition.
Yes.
So the data is very short, and also you cannot simulate the signals that you use to train your model. How it could be applicable, this
yeah, that's a very good question. You know, brain is a very complex system. And honestly, there is no lack of fundamental data available, but our weakness is we don't have the appropriate tools to to capture data, right? You know, in the brain of each of us, every second, you know, trillions of bits of information is transferred, right? And that information is really there. And we can measure that information in vitro, but not in vivo. which makes it useless, right? So we don't have good techniques to read from brain with high resolution. And I mean, we can try to come up with a simulation, and it is helpful, but I mean, it is tricky. I think you know about this, that the brain of a lot of simple species are already completely mapped. Like, for example, fruit flies and a bunch of other species. That may be used for simulation if you have like more detailed mapping and details. That may potentially help you understand what's going on in the brain of this fruit fly. But for humans, it is very sophisticated, you know, and I'm not expert in this area. I mean, there may be other experts here. Maybe we can ask them. Okay. Okay, let's take this last question and then move on. Yes.
Hello, Professor. Thank you for your slides. My question is, what is the role of differential equation B in the multimodality? The role of partial differential equation.
What is the role of differential equations?
Yes.
Right. I see. Thank you so much. I mean, I don't know what is the role of differential equations in multimodality, but I see there are two use cases of differential equations in AI. One is the fact that for you, in order to model a lot of physical systems, you will need to use differential equations. Like if you want to analyze a solid or the behavior of some liquid, you know, they follow differential equations. So that's a way to handle certain types of modalities. And also there are some ideas taken from differential equations into AI, right? For example, the idea of having 30 layers in a transformer model and in every layer adding some residual, you know, that has kind of been inspired from differential equations. Yeah, but we can discuss more after the talk. Okay, thank you very much.